The area increment r dr d theta arises naturally when we subdivide region described in polar coordinates by partitioning our theta and r intervals. This is related to something we call the Jacobian, which is a much more general idea related to transformation of coordinates. Now we know that our area increment in x and y would be delta x delta y, or dx dy. In polar coordinates we've seen it's r dr d theta. In general, if we have one set of coordinates that can be expressed in terms of another, then there's a calculation called the Jacobian, a quantity called the Jacobian, that represents how areas transform between one coordinate system and another. Now, writing x equals r cosine theta and y equals r sine theta, we've implicitly expressed x and y as each as a function of two variables, r and theta. So we could make that explicit by saying we have x of r theta equals r cosine theta, and y is a function of r theta, which is equal to r sine theta. The rate of change of x with respect to r is what? Now, first of all, what do we mean by the rate of change of x with respect to r? Well, if we change r by a little bit, that's going to change x by a little bit. Similarly, if we change theta by a little bit, we're going to change x by a little bit. And a small change in r, small change in theta will each entail a small change in y. So that x changes at some rate with respect to r and at some rate with respect to theta, and the same can be said for y. The rate of change of x with respect to r is just what we've become familiar with as the r derivative of x, and that's just cosine theta. The rate of change of x with respect to theta is just our theta derivative, which is negative r sine theta. And we can make similar statements about the derivatives of y with respect to r and theta. The y derivative is what? Derivative of r sine theta with respect to r is just sine theta. And the derivative of y with respect to theta is r cosine theta. Now we know our area increment in rectangular coordinates is dx dy. With respect to polar coordinates, it's r dr d theta, and we understand the reasons for both of these at this point. The question is, how do these area increments transform if we go from one coordinate system to the other? Now, the notation I'm going to use here is perhaps a little difficult to relate to what we're doing, but I'm going to put it down here anyhow. It's kind of like a partial derivative of our xy coordinate system with respect to our theta coordinate system. Now, in terms of what we just talked about, we have expressions for the rate at which x and y change with respect to r and theta. So this isn't particularly difficult to understand in that sense. We're taking the partial derivatives of x and y with respect to r and theta in a certain way that's going to allow us to relate these area increments. And the definition of this thing is nothing but the determinant of the matrix x sub r, x sub theta, y sub r, y sub theta. Now, writing that down in determinant notation, that's just the determinant cosine theta negative r sine theta sine theta, r cosine theta. To evaluate a determinant, we multiply this by this and this by this. We subtract this product, we subtract this product from this product. When we do that, we find that the determinant has value, in this case, simply, well, we have r cosine squared theta minus negative r sine squared theta. And that's just r. The result is that in terms of dr and d theta, our area increment has to equal the Jacobian multiplied by dr d theta, so that our r goes here, our r goes here, and we can write, come over here a little further, dA equals the Jacobian. And let me go back and introduce just a little extra notation here. I think at least one of your textbooks uses this notation. Okay, I'm going to call this the Jacobian, J of r theta, and it's equal to this quantity, so that we can say that the area increment in polar coordinates our dA is equal to the Jacobian times dr d theta. Written out more completely, the Jacobian can be written as sort of the partial derivative of x, y with respect to r and theta times dr d theta. Shortly we're going to go into volume integrals, where we have to describe all coordinates in all points in terms of three coordinates. We have different coordinate systems, and we're going to be able to generalize this idea of the Jacobian, this transformation of areas, and at the end of the chapter we'll try to make even more sense out of the idea. For right now, we can understand that our area increment r dr d theta is a result of a more general type of transformation of areas.